right. So let me just take a moment or so to introduce myself. I'm Professor Masoni. During the course of this semester, we're going to learn all about organic and biological chemistry. At least have a good introduction into it in many different areas. I know we haven't had, too long of class. We've only had essentially class for 2 days, but one of the reasons why I wanted to, get started with our office hour sessions right away was to use the opportunity to discuss not only some of the introductory topics that you find in the acid-base chapter, but to use that as sort of a discussion tool to discuss some of the aspects of chemistry that you hopefully do know about, and if not, maybe need a little bit of refresher of coming into the class. Organic chemistry and biochemistry are essentially second and third level areas of chemistry. There is sort of an understanding that you have some knowledge of chemistry coming into the course, and you don't have to know everything about general chemistry and such like that. But as you've already seen going through the notes, and as you'll see if you're with us tonight or watching this video, there are some aspects of chemistry that you should know coming into the class, okay? So as I said, for those of you joining us, if you have any questions at any point, feel free to use the chat feature, and also feel free to chime in with the audio as well. All right, so without further ado, let's sort of dive right into it. So in terms of acids and bases, there are two main definitions that we have to make you aware of. The first one is the Arrhenius definition of acids and bases. And Arrhenius essentially talks about what a substance does and I apologize, sometimes the pen writes really well and sometimes it doesn't. So what a substance does upon what is known as dissociation when dissolved in water. So in other words, you take a substance, you place it in water, it dissolves in water, but not only does it have to dissolve in water in order to sort of apply an Arrhenius definition, but it also has to dissociate when dissolved in water. So what do we talk about when we talk about dissociation? Dissociation refers to the separation into ions. Just because a substance dissolves in water doesn't mean that it dissociates. There are some substances that dissolve in water and stay as whole molecules. So that substance dissolves, but it doesn't dissociate. And there are other substances that not only will dissolve in water, but when they dissolve in water, they separate into ions. So not only do they dissolve, but they dissociate as well. Now, hopefully, you're familiar with species which are known as ions. Ions are similar to atoms in the sense that they essentially are made up of protons, neutrons, and electrons. But if you take a look at atoms, all atoms are neutral. So for an atom, the number of protons is always equal to the number of electrons. It doesn't have to be equal to the number of neutrons, because remember, your protons have a +1 charge and your electrons have a -1 charge associated with it. But all atoms are neutral. Now, how does that compare to ions? Well, ions have an overall charge. And the reason they have an overall charge is because here, the number of protons does not equal the number of electrons. Depending on which one you have more of will determine whether the ion has a plus charge or a negative charge. If you have more protons than electrons, the ion is going to have a positive charge. If you have more electrons than protons, the ion is going to have a negative charge. And the common charges that you come across for ions are +1, +2, +3, -1, -2, -3, and such like that. So for Arrhenius, in order for a substance to for us to look at an Arrhenius application, not only does the substance have to dissolve in water, but it also has to dissociate in water. Now, that's not all of it. Now comes the comparison of what we see for an acid versus a base. For an acid, one of the products upon dissociation is a proton. And we'll talk about the idea of a chemical reaction and products in a few moments, because I want to spend a little bit of time talking about that as well. But in terms of the Arrhenius definition, when the substance dissociates upon dissolving in water, one of the products upon dissociation has to be a proton. And when we think about a proton has a chemical symbol of H+. Or if you sort of looked ahead in the notes a little bit, another way that we can represent the formula of a proton is as H3O+, because once you generate a proton in water, you actually get a sort of a chemical reaction where the proton and the water combine to give you H3O+. But when you're looking at the Arrhenius definition, more often than not, the form of the proton you're looking for in the product is H+. You're not really going to see in the Arrhenius definition H3O+ as one of the products upon dissociation. You're more likely to see H+. Now, how does that compare to what Arrhenius talks about for a base? Well, here, one of the products upon dissociation is the hydroxide ion. And there's a specific formula for the hydroxide ion. The hydroxide ion has the formula of OH-, okay? So not only does it have to dissolve in water, not only does it have to dissociate when dissolved in water, but in order to be classified as an acid or a base, you have to have one of these two products. You have to have H+, or you have to have OH-. You're going to have one of them, not the other. Now, what if you have neither one? Well, then, according to the Arrhenius definition, the substance wouldn't be classified as an acid or base. More often than not, the substance would be classified as a salt, more likely than anything else. All right. Now, in terms of acids and bases, you don't have to memorize names and formulas. In other words, I gave you some examples of common ones like hydrochloric acid and sulfuric acid, or sodium hydroxide or potassium hydroxide. You don't have to memorize their names and formulas. But one of the expectations that I do have is that if you look at a chemical reaction, you should be able to tell, according to the Arrhenius definition, whether that substance is an acid or a base. So let's take a look at an example. And what we'll do with this is we'll have a little bit of discussion about chemical reactions and what are the pieces of them. Essentially, and I should say really chemical equations. Chemical equations are the shorthand notation for chemical reactions. So we want to discuss a little bit about chemical equations. So let's take a look at this substance, HNO3. here's the chemical equation for what happens when you take HNO3 and you place it in water. Okay. So, chemical equation. Most chemical equations have a single arrow indicating a reaction. Other chemical equations have a double arrow. We'll talk about what both represent in a moment. In either case, whether it's a single arrow or a double arrow, what you start with is usually on the left-hand side. Okay, so in this case, what you start with is HNO3. And the technical term for what you start with in a chemical equation or in a chemical reaction are what are known as reactants. There could be one reactant, there could be multiple reactants. In this case, there's a singular reactant, and that's what we start with. On the right side of the arrow or the double arrows are what we end up with. And the more specific term for what we end up with in chemical reactions and what you see on the right-hand side of chemical equations are what are known as products. Okay, so you have your reactants, what you start with, and you have your products, what you end up with. Now, if you have a single arrow in the chemical equation, that means that all the reactants are converted into products. But if you have a double arrow, what that means is that not only are reactants being converted into products, but some of those products are actually reacting with each other to reform the reactions. Like the arrow shows, like a two-way street. It goes back and forth, back and forth, back and forth. The term that we often use when you have reactions that have a double arrow, and we'll get into this either later on this evening or next time that we speak, is what is known as equilibrium, or what are known as equilibrium reactions. So single arrow, all the reactants are converted into products. The products do not react with each other to reform reactants. If you have a double arrow, then not only are reactants converted into products, but products are converted back into reactants as well. All right, so that's a little bit about chemical equations. One more thing, sorry, I forgot to mention. In some chemical equations, whether you have a single arrow or double arrow, there might be the chemical formula of a substance written above the arrow. When you have that, that indicates that that substance is behaving as a solvent. And hopefully you've heard of solutions before. In fact, when we get on into chapter 11 and going forward from there, we'll talk a little bit more about solutions. Well, actually, I shouldn't say that. We'll talk about them more in this chapter as well. But remember, when you make a solution, you dissolve a solute into a solvent. And essentially what we're doing here in the Arrhenius definition is that we're making essentially what are known as aqueous solutions by taking these substances and dissolving them in water. Okay? All right, so that's now all about chemical equations. Now, here's the ultimate goal. The ultimate goal is that you should be able to look at this equation and tell whether, according to the Arrhenius definition, this substance is behaving as an acid or a base. So first off, let's look at the product side. Notice that the products are ions. So dissociation has occurred. We'll assume that it has dissolved in water. It has dissociated into ions, but what's the key ion on the product side that's going to give us our answer here? It's the fact that one of the ions produced is H+. And because H+ is one of the ions produced, it tells us that HNO3, according to the Arrhenius definition, would be classified as an acid. Okay. Let's take a look at one more example. Let's look at the equation for what happens when you take a compound which has the chemical formula of Ca parentheses OH2, and you place it in water. Okay. So we're taking this compound, which is known as calcium hydroxide, the HNO3. And I didn't want to say the name because the name would have been a giveaway. HNO3 is nitric acid. Okay. CH parentheses OH2 is what is known as calcium hydroxide. Probably another giveaway as well, but let's do the work we need to do. So again, we don't have to memorize it as an acid or base, but by looking at this equation, we should be able to tell whether it's an acid or a base. So first off, I look at the equation, I see that when I take it, I place it in water, dissociation has occurred. Because the products are what? The products are ions. But on the product side, which is the key ion that forms that tells us whether we're looking at an acid or base here? It's the fact that one of the ions that forms is OH minus. Now, there are actually 2 moles or 2 equivalents of OH minus that form because chemical equations have to be balanced. I'm not going to go into that so much. Hopefully you know a little bit about that. But irregardless of whether there's a no number, which means 1, like you had on the previous slide, so there would be a 1 here if there's no number. Whether there's 2, whether there's 3, doesn't make a difference. It's the fact that we are generating OH minus on the product side of this equation. And therefore, that tells us that according to the Arrhenius definition, this substance would be classified as a base. Okay, so that is the Arrhenius definition of acids and bases. Okay. The second definition of acids and bases that we have to become familiar with is the Bronsted-Lowry definition. Okay. A couple things about the Bronsted-Lowry definition as compared to the Arrhenius definition in general. First off, the Bronsted-Lowry definition is more expansive than the Arrhenius definition. There are more substances that fit the category of being an acid or a base in the Bronsted-Lowry definition than there is in the Arrhenius definition. And the substance that comes to my mind always right away is ammonia. You know, you might be familiar with the fact that ammonia is a base. Ammonia is not a base according to the Arrhenius definition, because when you take ammonia and place it in water, it doesn't dissociate into ions. But ammonia is nevertheless a base because ammonia does fit the Bronsted-Lowry definition. So the Bronsted-Lowry definition is essentially more expansive than the Arrhenius definition. The other key concept is that when you look at the Bronsted-Lowry definition, you're usually looking at chemical equations that have 2 reactants. One of them behaving as an acid, the other one behaving as a base. And if you looked at the notes, and we'll talk about this a little bit as well, the products, if you have a reversible reaction with the double arrow, the products could be behaving as acids and bases as well. In the Arrhenius definition, you look at a singular reactant and what it does when you place it in water. But in the Bronsted-Lowry definition, you look at 2 reactants and you see, or you try to figure out, of course, which one is behaving as the acid and which one is behaving as the base. Okay. Now, according to the Bronsted-Lowry definition, what defines an acid? An acid is a proton donor in a chemical reaction. Okay, So in a reaction involving multiple reactions and looking at the Bronsted-Lowry definition, the acid is going to be a proton donor. Okay, an acid is a proton donor in a chemical reaction, where on the other hand, a base is a proton acceptor in a chemical reaction. Okay. So an acid is a proton donor in a chemical reaction. A base is a proton acceptor in a chemical reaction. And remember, for your Bronsted-Lowry, and we'll do a couple of examples, but in your Bronsted-Lowry world, you're going to have two reactants. One will be the acid, the other will be the base. Now, one of the key things to sort of help determine whether the substance is behaving as an acid or a base in the Bronsted-Lowry definition is to look at what it becomes. And essentially, in a Bronsted-Lowry reaction, the acid and the base become their conjugates. If you saw the notes, you know or saw that conjugates differ by one proton, one H plus. Okay. So two species, and so they use the term species sometimes, two species that differ by one proton are considered conjugates of each other. Now, an acid becomes its conjugate base. What's the difference between an acid and the conjugate base? The conjugate base has one less proton. Whether it's on the reactant side, or if you have the double arrow, whether you're looking at the product side, the acid on that side is going to become its conjugate base on the other side. How does it do that? It does that by, in this case, by donating a proton to what it's reacting with. In other words, it donates a proton to what it's on the same side with. On the other hand, a base becomes its conjugate acid. And what's the difference here? The conjugate acid has one more proton. The base is going to accept a proton from what it's on the same side with. And therefore, it's going to become its conjugate acid. And by doing so, it's going to have one more proton. So those are the relationships that are present. All right. So actually, I'm going to go to the textbook and I'm going to take a look at problem 1074. I'm going to look at it a little bit differently than what they have here. But let's do a couple different things. First off, let's do the following acids, and let's come up with the formula for the conjugate bases. And the two acids we're going to look at here is HS minus and H3O plus. Now, the way that I described it in the lecture notes, and the way that I would do this is that I would take out, so if we're going from an acid to a conjugate base, the conjugate base is going to have one less proton. I'm going to take out the proton in two steps. I'm going to take out an H from the chemical formula, and then to the charge, I'm going to take out a +1 from it. Now, one of the things that I think helps in terms of figuring out the charge is to remember your number line. Okay, so if whatever the charge is, if we're taking out a plus from it, which direction, if you're looking at the number line the way I drew it here, which direction are we going to be moving? We're going to be moving one direction to the, and I always do that. I point and it's going the wrong way when I look at it on the screen. Anyways, it's going to be going this way. All right, it's going to be getting, the charge is going to be getting smaller, one smaller, so to speak. Okay. All right, so first example, HS minus. So how many hydrogens are there? There's only one. If I take one out, I'm left with none. But I still have the sulfur. The charge is -1. If you have for an ion, if you have a plus or minus with no number, that means either +1 or -1. So the charge is -1. If the charge is -1 and I take out another positive, what does the charge become? The charge becomes -2. And sometimes I circle the charge, sometimes I don't. It's just me. So the conjugate base would be S-2. That would be the conjugate base here. All right. H3O plus. All right. So again, we're going to take out an H. Now in this case, there are 3 hydrogens that are there. If I take out 1, I still have 2. Nothing happens with the oxygen. So as of now, I have the formula of H2O. I took out an H. There were 3 of them. I'm now down to 2. So I have H2O. Now, the charge was +1. That is a positive. Okay. So the charge is +1. If the charge is +1 and I take out a positive charge, what does the charge become? The charge becomes 0. So I don't write anything as a superscript. So the correct formula for the conjugate base here would be water, H2O. All right. So those are some examples of acids to conjugate bases. Let's go the other way around. Let's do base to conjugate acid. And the 2 examples we'll take a look at are NH3 and HCO3 minus. Okay. So now, the way I like to do it is still in 2 parts. But now, instead of taking out an H and a plus, now I'm going to put in an H and a plus. Okay? So for NH3, I start with 3 hydrogens. I'm going to put 1 in. So how many am I going to have total? I'm going to have 4. So the NH3 becomes NH4. The charge in NH3 is 0. There's no superscript. So the charge is 0. So now if you go back to the number line here, if I'm putting in a plus charge, which direction am I going to move? I'm going to move one space this way. So if the charge is 0 and I put in a positive, what does the charge become? The charge becomes +1. NH4 plus would be the formula for the conjugate acid. All right. HCO3 minus. So there's one hydrogen. I'm going to put another one in. So I go from having one hydrogen to now having how many? 2. In the first example, nothing happens to the nitrogen. In this example, nothing happens with the carbon, nothing happens with the oxygen. Okay. But I go from having one hydrogen to now having 2. So instead of having HCO3, I now have H2CO3. What about the charge? The charge in HCO3 is -1. If I put in a plus, what does the charge become? The charge becomes 0. So H2CO3 would be the formula for the conjugate acid. All right. Okay. So with this being said, let's take a look at a couple of examples, an example or two. Let's see, of Bronsted-Lowry reactions to identify the acid and base. And again, if you have any questions, feel free to jump in with the audio, or you can type something in the chat as well. So sometimes they don't have stuff in the back, which is sort of a problem. So let me just see if I can find something here good. Okay.
Professor?
Yeah, go ahead.
Hi, sorry, I just was curious. Do we need the textbook for this class, or can we find all of this in Canvas?
So you're gonna need a copy of the textbook.
Okay.
The homework problems are assigned from the textbook.
Okay.
My recommendation, though, would be to get the e-copy of the textbook from where I posted via the announcements. I think that would be the cheapest version.
Okay.
But yeah, you will need a copy of the textbook for the course.
Okay, thank you.
Of course. All right.
Professor, can
Yeah.
you tell me what page the homework is on?
So
Because you posted homework.
So
Yes.
the homework problems are found throughout the chapter. So there's no specific page that the homework is on. So when you look at the syllabus, you'll have a page that has the the tentative schedule with dates, and then the topics, and then the homework problems.
Yes.
The number in bold is the chapter number, and then the questions are after that. So for example, if you're looking at the chapter 10 homework, I believe the
Yes.
first problem assigned is
10-8.
Yep, 10.8. So what you do is you want to go to, let me just go back a slide. So what you want to do is you want to go and start with question 10.8, which is actually on page 330. Okay. So
330.
page in my textbook, they're on page, my textbook, it's on page 330, 10.8. So chapter 10, question 8. I have it on page 330.
Okay.
Let's see if I don't know if it'll come through clear. Yeah, that's what happens with the virtual screen. But yeah, that's where I have it. Some books might have it a little bit differently. You want to try to use the 13th edition. I believe the ebook is exactly the same as the hard-covered version. So you would find it on page 330, 10.8. And then the rest of the problems are found throughout the chapter. So they're not on one specific page.
Okay.
But they're labeled under, you'll see them, they're labeled under practice problems.
Okay. Thank you.
Of course. All right. Let me just go back. And if you have other questions like that, just please let me know as well. We can answer some of them for you. Try to sort through some of the other stuff. All right. All right, so let's go to here. All right, so the example I wanted to take a look at was, start with this one here. NH3 plus HNO3. And then on the product side, we're going to have NH4 plus, and we're going to have NO3 minus. Okay, so the example here is we want to identify the reactants as acids and bases. And the reason why we only have to worry about the reactants here is because we have a single arrow in the equation, which tells me, will tell you as well, that the reactants are converted to products, but the products don't react with each other. The products don't react with each other. So in terms of behaving as acids and bases, all we really have to do here is we have to worry about the reactants, all right? So how would I do this? Well, I would start with the NH3. And the first thing I would do is I would say, okay, which one of the two products does the NH3 become? Does it become the NH4 plus, or does it become the NO3 minus? The NH3, and how do I know which one it becomes? Remember, Bronsted-Lowry definition, what do you become? You become your conjugate. And remember, conjugates only differ by one proton. So the only product that the NH3 could become is the NH4 plus. So that's the first part of it. The second part of it would be, what did it do to become that? Did it donate a proton to the NH3? The HNO3, did it donate a proton to the HNO3? Or did it accept a proton from the HNO3? And remember, very important, you only donate and accept with what you're on the same side with. In order for the NH3 to become NH4 plus, it had to accept a proton from the HNO3. And therefore, the NH3 would be classified as a base. So that's the NH3. Okay. The HNO3, same thing. Okay. Which one of the two products does the HNO3 become? Does it become the NH4 plus, or does it become the NO3 minus? Well, based on the idea of conjugates, the HNO3 has to become NO3 minus. How does it do that? Does it do it by donating a proton to the NH3 or accepting a proton from the NH3? It does it by donating a proton to the NH3. And therefore, it would be classified as an acid. And again, we don't have to worry about the product side in this particular case because we only have a singular arrow. So the reactants will convert to the products, but the products will not convert back to reactants. All right. So that's our first example. Let's take a look at one more. Let's take a look at this one here. So we've got H2S plus H2O. Now this time we're going to have a double arrow, and we're going to have H3O plus, and the other product will be HS minus. So now, let me see if I can erase that. So now, because I'm dealing with a double arrow, not only am I going to classify the reactants as acid and base. But since the reaction occurs, since the products are going to react to reform the reactants, I want to classify the products as acid and base as well. Let's start with the reactants first. So for the reactants, we're going to do the same thing like we did in the previous example. If I start with the H2S, which one of the two products does the H2S become? Based on the idea of conjugates, it has to become the HS minus. Now, how does it do that? Does it do that by donating a proton to the H2O or accepting a proton from the H2O? It becomes HS minus by donating a proton to the H2O. And therefore, the H2S would be classified, I'm not sure what's going on. So let's see. Okay, there we go. Would be classified as an acid. Okay. For the water, which one of the two products does the water have to become? Well, based on the idea of conjugates, the water has to become H3O plus. How does it become H3O plus? By donating a proton to the H2S or accepting a proton from the H2S? It accepts. And therefore, it would be classified as a base. Now, how would we handle the product side? To handle the product side, we would do the same thing like we just did, but we want to go in the opposite direction. So if I start with the H3O plus, I want to say, okay, which one of the reactants must the H3O plus become? Now, again, how do I know that? Again, it's still based on the idea of conjugates. So the H3O plus has to become H2O. Can't become H2S. It has to become H2O. Now, how does it do that? Does it do it by donating a proton to the HS minus or accepting a proton from the HS minus? And again, you only donate and accept protons with what you're on the same side with. The H3O plus becomes H2O by donating a proton to the HS minus. And therefore, the H3O plus is an acid. And then finally, for the HS minus, okay, which one of the two reactants must the HS minus become? It has to become H2S. How does it do that? Does it do it by donating a proton to the H3O plus or accepting a proton from the H3O plus? It does it by accepting a proton from the H3O plus. And therefore, it would be classified as a base. If you do this correctly, the acid on one side and the base on the other, just by looking at their formulas, chemical formulas, should be conjugates of each other. You know, if you put acid here and base here, and these two are not conjugates of each other, this and this, it's not right. So the acid on one side and the base on the other must be conjugates of each other. And when you have these reactions with double arrows, you have essentially two conjugate pairs. In this case, you would have H2S and HS minus, and you would have H2O and H3O plus. And a lot of times with these Bronsted-Lowry reactions with the double arrows, you classify the conjugate pairs, or you state, I shouldn't say classify, you state what the conjugate pairs are. Okay, so that's a little bit about the Bronsted-Lowry definition. All right, last thing for this evening, I want to talk a little bit and I don't know if I'm spelling the name exactly correct, but that's okay. I want to talk a little bit about what is known as Le Chatelier's principle and equilibrium. So for a chemical reaction to be at equilibrium. Two things must be true. The first is that the rates or the speeds of what are known as the forward and reverse reactions must be the same. Now, remember a little bit earlier on this evening in the video, we talked a little bit about how the double arrow in a chemical equation sort of indicates an equilibrium reaction. In reality, that's more of an assumption than a fact. The double arrow means that there is some conversion not only from reactants to products, but also products to reactants as well. For a chemical reaction to really be at equilibrium, the first thing that must be true is that the rates or speeds of the forward and reverse reactions must be the same. Now, when we talk about the forward reaction, we talk about the conversion of reactants into products. And when we talk about the reverse reaction, we talk about the conversion of products into reactants. If the two-way street, right, the double arrow, if the speed on those streets, one way and the other way, are exactly the same, that's one of the conditions that has to be true in order for a reaction to be deemed as being at equilibrium. The second thing that has to be true is that the concentrations or the amounts of the reactants and products must be constant. In other words, they are no longer changing. Now, the amount of reactant and the amount of product doesn't have to be the same. In fact, if you have multiple products, their amounts could be different. Whatever the amounts of reactant and products are for each of them, whatever they are, they have to be no longer changing. They have to be constant. If these two conditions are met, then you are truly at equilibrium. Okay. There are stresses that can be applied to reactions at equilibrium that will take the reaction out of equilibrium for a certain amount of time. The one we will look at is changing the amount of reactant or product. In other words, essentially physically by hand, putting reactant in or putting product in, or physically by hand, taking reactant out or taking product out. And not necessarily by hand, but but by physically doing it, doing something that alters the amount of reactant or product. Now, what happens when a stress is applied? Well, when a stress is applied to a reaction at equilibrium, the reaction shifts towards one direction. In other words, one direction initially, well, I should say initially, but now becomes faster than the other. To do what? To counteract that stress. Now, eventually, equilibrium will be reestablished. In other words, the rates or the speeds of the forward and reverse reactions will become the same again. And the amounts of the reactants and or products will no longer change, but the speeds and amounts will most likely be different than before. And, the one I'm definite about are the amounts. Now, with all of this in mind, what is the expectation that we have of you? Basically, the expectation that we have is we want you to be able to predict how the reaction at equilibrium is going to shift when a stress in terms of changing the concentration or the amount of reactant or product is applied. Just go to bottom line it, nice and simple. When we change the amount of reactant or product, you need to be able to tell how the reaction is going to shift. That eventually, and then at some, and then just knowing that at some point equilibrium will be reestablished. But when that stress is applied, how does the reaction shift to counteract that stress? Or I should say, in response to that stress. So, in terms of changing the amount of let's see if we can start that. Okay. In terms of changing the amount of reactant or product, there are 4 possible scenarios. right, so here's your stress. 4 possible scenarios. You could add product, you could add reactant, you could remove product, you can remove reactant. Here's the way I like to remember it. When you're adding, the reaction shifts in the opposite direction. When you're removing, the reaction shifts in the direction that you're removing from. So if you're adding, the reaction will shift in the opposite direction. If you're removing, the reaction will shift in the direction that you're removing from. So if you're adding product, the reaction will shift. And I don't know if we're going to be able to get that in. Sorry. All right. So if we add product, we are going to shift towards the reactants. Okay. If we add reactant, we are going to shift towards the products, right? Because if you're adding, the reaction shifts, and this is fact, the reaction shifts towards the opposite side. Okay. If we remove product, the reaction will shift towards the products. And if we remove reactant, the reaction will shift towards the reactants. All right, so these are your stresses, and this is the shift in reaction when stress is applied. Okay. So this sort of chart here is what you'll have to remember. And if you can sort of remember our shortcut idea, in terms of adding, it shifts towards the opposite side. If you're removing, it shifts towards the side you're removing from. That will make it somewhat helpful as well. All right. Let's see. So yeah, so let's just finish up by looking at an example, and then we'll be done for tonight. Okay. So let's take a look at the following reversible reaction. All right, so let's take a look at some stresses. And then let's take a look at the shift in reaction when stress is applied. A couple ones. All right, so here's the first stress. The first stress is let's remove some HClO. So if we remove some HClO, sorry. What are we doing here? Are we removing reactant or are we removing product? If I take a look at the equation here, the HClO is on the reactant side. So what am I doing here? I'm removing reactant. You have this reaction at equilibrium, okay? What's going to be the shift when the stress is applied, okay? If I'm removing reactant, the reaction is going to shift towards the reactants. Okay, so that would be our first stress. Right? Second, adding more ClO minus. So I have this reaction at equilibrium. I'm adding more ClO minus. How does the reaction shift? What am I doing here? Am I adding more reactant or am I adding more product? In this case, I'm adding more product. And because I'm adding more product, the reaction is going to shift towards the reactants. All right, let's do one more. Removing some H3O plus. Tough to see that. Let me write it again, which might make it even worse. But... So removing some H3O plus. So what am I doing here? I'm removing what? I'm removing product. And if I'm removing product, I have reaction equilibrium, I'm removing product, how's the reaction going to shift? It's going to shift towards the products. Okay. So that's the expectation of what I need you to be able to do. If you have this example here of a reaction at equilibrium, here are some stresses, and these are the shifts that would occur. That doesn't look very good. Let's write that again. And this was actually 10.86. I try to leave you the odd numbered ones because for the odd number ones, the answers are in the back. So just to let you know that. All right. And that's it for this evening. Okay. Any last minute questions before we say goodnight?
No, thank you very much.
Of course. Stay well. Hope to see you next week. I'm going to post a video to Canvas shortly, either later tonight or tomorrow. And any questions in between, just let me know. And we'll do the rest of acids and bases during the next office hour. All right.
Thank you.
Thank you.
Thank you. Thanks for
Have a
joining.
good night.
You too. Stay well.